One notion that will be useful to consider as we're factoring is the notion of the greatest common factor of two objects. Now, for integers, a common factor is just an integer that's a factor of both or all of the integers in question. The greatest common factor of two or more integers is the largest positive number that is a common factor. So here we're going to list all the positive factors of the integers 8 and 20. Right, so 8 is 1 times 8, so 1 and 8 are factors. It's 2 times 4, so 2 and 4 are factors. And that's really the only things we can multiply to get 8. So 1, 2, 4, and 8 are all of the factors of 8. 20 is 1 times 20, so 1 and 20 are factors. It's 2 times 10, so 2 and 10 are factors. 3 doesn't go into 20, but then 20 is 4 times 5, so 4 and 5 are factors. So 1, 2, 4, 5, 10, and 20 are the factors of 20. The largest number that appears on both of those lists we can see is 4, and so 4 is the greatest common factor of 8 and 20. Notice that 1 and 2 are also common factors, but among the common factors, 4 is the largest, the greatest, so 4 is the greatest common factor. If we want to talk about the greatest common factor of monomials or polynomials, well, we need to say what we mean by greater. The greatest common factor of two or more monomials is, well, it's a common factor, so it's a monomial that's a factor of both of them. And it's greatest in the following senses. 1, it has the largest possible coefficient, and 2, it has the highest possible degree. So every variable is raised to the highest possible power, and the coefficient is as big as possible. If we want to find the greatest common factor of some monomials, well, first we find the greatest common factor of the coefficients, and then we take the lowest power of each variable that appears among the monomials. So let's see what that looks like. To find the greatest common factor of the numbers, again, we can just think about all the factors of the numbers. Or if we factor them into primes, we can treat them like variables and just take the lowest possible power of each prime factor. So for the coefficient, if we want to take the greatest common factor of 3x to the fourth y to the third, 6x to the third y to the fifth, and 9x squared y to the seventh, well, the coefficients, 3 is already prime, 6 is 3 times 2, 9 is 3 times 3. Those are the prime factorizations. So we look at what those all have in common, which is just a 3. The GCF of the coefficients is 3. So the coefficient in our greatest common factor will be 3. For x, we have an x to the fourth, x to the third, and x squared. X squared is the smallest power, so our GCF will have an x squared. For y, we have a y to the third, a y to the fifth, and a y to the seventh. The smallest power is y to the third, so we have a y to the third. 3x squared, y to the third. And we notice that that really is a common factor, right? 3x to the fourth, y to the third. Well, that's 3x squared y to the third times, we need 2 more copies of x. 6x to the third, y to the fifth. Well, that's 3x squared y to the third times, let's see, we need to multiply the 3 by a 2. We need 1 more copy of x, and then we need 2 more copies of y. 9x squared y to the seventh. Well, we need to multiply 3x squared y to the third. We need to multiply the 3 by another 3. We don't need any extra copies of x, but we need 4 extra copies of y. So we see that that really is a factor of each of our 3 monomials. And looking at these 2 monomials specifically, we see that they don't have any factors in common. So there's nothing else that I could put into my 3x squared y to the third and get something that's a factor of those 2 at the same time, which tells me that I really do have the greatest common factor.